Back to temperature and heat. Temperature is the measurement that's proportional to average kinetic energy, and we also use things like pressure and volume and the number of molecules to typify or describe a state. And in fact, those are called the variables of state. So temperature is one of the variables of state. Those variables of state tell us about the macroscopic system, and we make calculations on them. Oh, I want to talk about this just because it's one person at least included this in their scrapbook. The Magnus force. How many people are into baseball at all? Okay, we got 2.5 or so. Well, one of the things that's really important in baseball is the pitcher making the balls hard to hit. Now, for people like me, if you throw it fast, it's hard to hit. But those guys are really good. And so they are able to track the trajectory of a ball and predict where the ball is going to go. That's a lot of physics right there. That's the physics that we studied for the first exam, where the ball is going to go once it leaves the pitcher's hand. Once it leaves the pitcher's hand, it's in free fall, right? And we, in this class, pretended that air makes no difference. If you just throw the ball, and if the ball was perfectly smooth, the air would slow it down a little but not make a lot of difference. But the ball's not perfectly smooth. So one of the pitches that people will use is a knuckleball pitch. A knuckleball pitch is a pitch that you throw using your knuckles instead of your fingers. The idea being you release it with a flick and there's no spin. If there's no spin, then the seams are going to catch air and cause the ball to move around kind of randomly as they catch the air. And so a knuckleball is hard to hit because nobody can predict where it goes. It's also hard to catch because the catcher can't predict where the knuckleball is going to go either. The pitcher throws roughly at the plate, and then the ball goes wherever it wants to go based on how it interacts with the wind. But when a pitcher throws a curveball, and I swear when I was a kid, a curveball meant something that curved like this or like this. Nowadays, when they say curveball, they mean a sinker ball, one that you throw snapping over the top, and instead of following the normal trajectory like this, it falls more. So they say his curveball falls off the plate or something like that, that it drops quite a bit below. And the reason for that is what we've been studying, this Magnus effect. The Magnus effect, you have the ball spinning, and because of the seams, it catches the air and makes the air move. So in this picture, a ball is shown traveling to your left and spinning like this. Now that's actually the opposite of the way a pitcher throws a sinker ball. This would be I guess a floater. I don't know that anybody throws that, because how would you throw that? You'd have to let it slide off your hand or something. It seems like a funny release. I guess if you're throwing sidearm, you could throw it like that. So this here, because it's pulling the air, it's going to pull more air up on top. Jamming more air up on top is actually going to make the air on top have a lower pressure, because it's going to be traveling faster there because it has a larger distance to cover. So you have lower pressure on top, a higher pressure on bottom, and that would push the ball up. Now, one of the things we had when I was a kid was a track ball. A little game you have. I actually still have it in my garage, except for all the balls are gone. But you have something kind of like a high-lie stick, and you use it to throw these lightweight balls, and you put a lot of spin on them like this, a backspin, and you can throw the ball, and you see it go zooming up, or you go like this, and it does a cool arc like that because of this Magnus effect. And so when a pitcher pitches a sinker ball, they're pitching it coming over, so their release is making it spin the opposite direction of this, which is going to jam the air down here and create the low pressure on the bottom. So the higher pressure on the top is going to push the ball down more than gravity would make it fall. Is this useful outside of baseball? Believe it or not, the answer is yes. They have actually made ships that instead of having a sail, they have a spinning cylinder. And if you have a breeze blowing and you spin the cylinder, it's going to create a low pressure region on one side and a high pressure region on the other, and you can use that to move the ship. And so they've actually done that, and my understanding is it was pretty efficient. Okay, now back into thermodynamics. I took this from a lower level physics textbook, and it used Comic Sans, or Comic Sans, whatever you pronounce it, for its font. Just have to tell you, I changed it back. So, first of all, temperature. We measure temperature by putting something in thermal contact. Thermal contact means that they can exchange energy. We call the energy exchange heat. So heat is an energy exchange. It is not energy. You don't possess heat. You possess thermal energy. But if I touch something, like I touch this, I feel cold. What I'm feeling is heat flowing out of my body. So the heat is the transfer of energy. So we measure temperature by bringing two things into thermal contact to make them so heat can flow. And then what we're actually measuring is the temperature of our thermometer. We're not measuring the temperature of the boy in this case, we're measuring the temperature of the thermometer in his mouth. But if we leave the thermometer in his mouth long enough, because they're in thermal contact, heat will flow. And we have a law of thermodynamics, the second law of thermodynamics, that says heat naturally flows from a hotter object to a colder object. So the heat will flow from the boy into the thermometer to warm up the thermometer until it reaches the boy's mouth temperature, and then we measure the thermometer's temperature. So, thermal contact. The easiest way to understand thermal contact is direct contact. If I have this Bunsen burner on and I touch it, we know when I touch it, I'm going to have a lot of heat that flows into me. That's not the only way to have thermal contact. If I put my hand above this, it's still going to get very hot, right? So that's also thermal contact, even though it's not physical contact. In that case, it's thermal contact through one of the other mechanisms of heating. Heating has three mechanisms that we will discuss more carefully later. Right now, just saying them. You have conduction, which is direct contact, which is what we usually think of for thermal contact. You have convection, which is an intermediary, is transporting the heat. So in this case, it would be the hot gas. Or you can have radiation, which is the same as light when it's electromagnetic waves. Yeah, go past that. Thermal equilibrium, we just finished a test that covered equilibrium. Equilibrium meant equal forces. Librium, force, equal. Thermal equilibrium is going to be the situation where instead of mechanical equilibrium, there was no acceleration. For thermal equilibrium, there's no heat flow. So if I bring two things in thermal contact and there's no heat flow, we say that's thermal equilibrium. And according to the second law of thermodynamics, if things are in thermal contact, so heat could flow, and they're in thermal equilibrium, so heat's not flowing, then they must be the same temperature. So that's another part of how we define temperature. So two or more objects in thermal equilibrium have the same temperature. That seems pretty obvious. So obvious that originally scientists thought it would be daft to make this a law. And so they made the first law of thermodynamics, which is a simple law that we've already discussed. Energy cannot be created or destroyed. Remember when we did the Defy Gravity Lab, you were using that idea for calculating how much energy was stored in the trampoline. So that's the first law. The second law, like I just stated, says in one of its statements, there's like 3 or 4 statements of the second law, that heat spontaneously flows from something at a higher temperature to something at a colder temperature if you put things in thermal contact. The third law, just for completeness, is that nothing can reach absolute zero. And then they said we should have put this in. And so it's more fundamental than the rest because it's defining something about temperature, so they call this the 0th law of thermodynamics. So thermodynamics, you don't start counting at 1, it's like computers, you start counting at 0. And the 0th law of thermodynamics says if 2 or more objects are in thermal equilibrium, they have the same temperature. The actual statement is if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. Which, putting into English, means, okay, in thermal equilibrium with means temperatures are equal. So if temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C. That's putting into standard English. And it seems real obvious. But as they started understanding temperature more precisely, understanding that it's actually the result of the derivative of energy with respect to entropy or something like that, like, whoa, that wasn't as obvious as we had thought when we started. And we're not going to get into that definition of temperature in case you're worried. Not even people in the calculus class. So here's two objects in thermal contact. Thermal contact meaning energy can pass between them in the form of heat. What's the difference in heat and work? Work is energy transport, right? But work had a force times the distance. It involved motion. Heat doesn't involve motion. So with thermodynamics, we're going to have both ways of transferring energy. One with work involved, one without work involved, and one without work, heat. So here we have two things in thermal equilibrium, and it shows an arrow with Q. Q is our symbol for heat now. So Q equals heat. Heat is flowing from this object to this object. What does that tell you about the two objects? Okay, they're not in thermal equilibrium, which means they're not the same temperature. And which one is hotter? Okay, the red one. Now, I have 3 students here who are in astronomy, so they're a little ahead of you on this. In terms of temperature, what color tends to be hotter, blue or red? Blue. So the colors here are a little misleading because if you were to gauge by the colors, you would say the blue one's the hotter one and the heat should be going the other direction. But it's actually going from the red to the blue because, well, they just mislabeled them. A really simple question. If I have a little tiny BB that's heated up means we put energy into it, to a temperature of 200 degrees Celsius, and I put in water that's 30 degrees Celsius, which direction is heat going to flow? From the big cup of water into the little BB, or from the little BB into the big cup of water? BB into water, because the rule has nothing to do with the total energy, it's the average energy, it's the temperature. Now, I need to specify, I keep talking about temperatures to average kinetic energy. It's proportional to the average kinetic energy, but the proportionality is different from one material to another. So two objects at the same temperature are not going to have necessarily the same average kinetic energy because there's different proportionality depending on the object. Okay, we've talked about everything here. Heat, if you add heat, it increases the temperature because you add heat, you're adding energy. The average kinetic energy goes up, temperature goes up. That's pretty obvious. So everybody understand heat and temperature are not the same? Let's talk about units. Thank you, Ryan. I was telling somebody yesterday. It's good to have Ryan in class because he will answer questions. Sometimes he's not right because you know what? He's human. If you're right every time, what should you not be in this class? Right? It'd be dumb to take the class if you knew all the answers. So I appreciate you answering the questions for me. Hey, I want to be like Ryan.
Yeah.
See. Okay. What are the units for heat? I've said heat is a measurement proportional to kinetic energy. Well, actually, temperature is proportional to kinetic energy. Heat is transfer of energy. Sorry to get myself confused. The proportionality means that it could have different units, but heat is a transfer of energy. So heat's units, what should they be? It should be joules. That should be the SI unit. Now, it turns out we have another set of units that we use for it. Calories. But calories are just another unit for heat. There's a direct calculation, 4.186. You'll find books with different numbers. Chemistry often uses 4.184. But 4.186, was it 4.186 calories is joule or joules per calorie? I'd have to look to see which way it goes. But there's a direct correlation between them. So the units of heat are units of energy. Units of temperature they're not going to be units of energy. They're related to energy, but they're not units of energy. So let's talk about those units. So here I have a thermometer with the Celsius and the Fahrenheit scale. Real quick history. Was it 1724? Gabriel Fahrenheit developed his Fahrenheit scale. His Fahrenheit scale, we write here that it has a freezing point for water of 32 degrees Fahrenheit and a boiling point for water of 212 degrees Fahrenheit. So the difference between boiling and freezing is 180 Fahrenheit degrees. Technically, if you're talking about a change, you put the degree sign after. If you're talking about the actual temperature, you put it before. Nobody pays attention to that technicality. So 180 degrees between freezing point of water and the boiling point of water. Why 180? Why would he choose that number? He didn't. His calibration points, I have heard different definitions, but we'll just go with 100 degrees Fahrenheit was the temperature of a cow. Measured by temperature of cow, that was 100 degrees Fahrenheit for its calibration. And 0 degrees Fahrenheit, the temperature of ice mixed with ocean water where he lived. So it was based on a difference of 100 degrees. We call that a centigrade scale because centi 100. That was his calibration. The problem is those calibration points are not very reproducible. A cow could go in heat. When I worked at the dairy, we had these little thermometers that we would put on the cow's rumps to measure their body temperature. And if their body temperature goes up, they're in heat, which means that it's time to get them getting pregnant. So it's not a good calibration method. Furthermore, the salt water. Well, if you go to a different part of the ocean, you have a different concentration of different things, and it's going to have a different freezing temperature. So those aren't really good calibration points. So just a few years later, a good old Swede, Anders Celsius, I'm sure his name is pronounced something like Anders, developed his own scale. And Celsius used the temperature of freezing, pure freezing water and pure boiling water, which is great because pure boiling water at 1 atmosphere pressure is always going to boil at the same temperature. And pure freezing or pure water will freeze at 1 atmosphere at the same temperature. Now, Anders Celsius, I was looking this up before class, he, for some reason, said that 0 degrees Celsius is the temperature of boiling water, and 100 degrees Celsius is the temperature of freezing water. It seems odd, doesn't it? Yeah. Just 1 year later, independently, another physicist, and I can't remember his name, came up with a scale that had 0 degrees Celsius is the temperature of freezing water, and 100 degrees Celsius, well, not Celsius, okay, 0 degrees and 100 degrees with them flipped. Well, Celsius died in 1742. And then when he died, Linnaeus said, okay, Celsius scale, we're going to reverse it now to make it make sense. So the Celsius scale only had 0 degrees Celsius with boiling water for 2 years, and then it got flipped. So now 0 degrees Celsius is the temperature of freezing water, and 100 degrees Celsius is the temperature of boiling water. So there's a difference of 100 Celsius degrees for the same scale that was 180 Fahrenheit degrees. 180 divided by 100 is 9 divided by 5. So the change in Celsius is, compared to the change in Fahrenheit, is just 180 over 100 or 9 to 5. And then we have an offset, 0 Celsius is 32 Fahrenheit. So putting those two things together, we can come up with a simple calculation to convert between Fahrenheit and Celsius or between Celsius and Fahrenheit. You take the Fahrenheit and subtract 32 because of that 32 degree offset, and then you multiply by 5/9 to get to Celsius. To go the other direction, you just take the Celsius temperature, multiply by 9/5, and then add the 32 for the offset. So it's easy to translate between the two. Now, one more thing about the Celsius scale. I talked about the calibration points. I thought that the conversion occurred in the 70s, but what I was reading this morning said it occurred in 1948 or 1954. somewhere before I was born. Let's put it at that. So somewhere in the really dark ages. The definition of the Celsius scale was changed. So no longer is it defined by 0 and 100 degrees Celsius. It's now defined so that absolute 0, which we haven't talked about that concept yet, is minus 273.15 degrees Celsius. That's a definition for calibration. And the triple point of water, oh, that was off. That was not intended. The triple point of water, I'm going to have to just write it above because of water is 0.01 degrees Celsius. So it's not a centigrade scale anymore either, because it's not based on a calibration broken into hundreds. So those are our two common scales. And which one is the standard for science? Somebody said meter, he said Kelvin. Kelvin is the standard. What's the difference? Well, the difference is there is this thing we call absolute 0. Oh, yes, I have to point that out. Celsius and Fahrenheit are both exactly equal at 40 degrees, minus 40 degrees. So physicists like to make stupid jokes like, whoo, it's minus 40 degrees out. Is that Celsius or Kelvin? Or Celsius or Fahrenheit? Because it's the same, right? We've got great senses of humor. You should not mess with our humor. Okay. Absolute scale. Because temperature is proportional to kinetic energy, there is an absolute minimum to kinetic energy. What's the lowest kinetic energy you can have? ½ mv squared. What's the lowest you can get with ½ mv squared? 0. If V goes up, it's going positive. So the idea of absolute 0 comes from the idea that proportional to average kinetic energy, there's an absolute minimum to kinetic energy, hence there must be an absolute minimum to temperature. Now, there's some quantum dynamic or quantum physics that plays into this, and we're not going to talk about that. But there is an absolute 0. On the Celsius scale, it's minus 273.15. On the Fahrenheit scale, it's minus 459.67 degrees Fahrenheit. The Kelvin scale is an absolute temperature scale. By absolute, it means that there's no negative values. It's just taking the Celsius scale and shifting it by that 273.15. So absolute 0 is 0 kelvins, and then any temperature is just the Celsius temperature plus 273.15. So water freezes at 0 plus 273.15 is 273.15 kelvins. Notice we don't use the word degree with kelvins. And water boils at 373.15 kelvins. I put this in here. I know we don't have clickers, but I thought it's a great question. It's kind of tricky. Let's just go through each one. True or false? Was the Celsius scale developed by a Swede?
True.
True. Who else is a Swede in this classroom? I'm a quarter. How much are you, Mira? An eighth. Ha. If we were in astronomy, of course, Alex is more Swedish. It is the centigrade scale. True or false?
True.
We've got some variation here. Initially, it would have been true because 0 degrees is the temperature of boiling water and 100 degrees is the temperature of freezing water. It's a difference of 100 degrees. After Celsius died, it was turned over by Linnaeus. It was still 100 degrees, so it's still centigrade. But now, it's no longer calibrated by the 100 degrees, so it wouldn't be a centigrade scale by the definition of calibration. You could still say, well, it's still 100 degrees between boiling and freezing, so it's still centigrade in the original sense. Dr. Osborne and I were having a discussion about if this one should be considered true or false. Originally, 0 degrees Celsius was the temperature of boiling water. True or false? True. For 2 years. It's an absolute temperature scale. False. False, because 0 is minus 270, or absolute 0 is minus 273.15. And it's the SI unit of temperature?
Also false.
Also false. All right, now for fun stuff. Temperature measurement. When somebody puts the thermometer in your mouth, it's getting to be the temperature of your mouth. And what do you see on the normal thermometer? Well, what tells you the temperature when you read a normal thermometer? I know you know this answer, but I do want you to respond.
What do you say?
How do you determine the temperature on a normal thermometer?
The red stuff inside. That points it in.
Okay, the red stuff inside. You read the meniscus. Yeah, those are the kind of answers I was looking for. The reason everything's legged today is because my hose was leaking. I had to go get a new hose. Not my excuses. So I'm going to measure temperature here, but I'm not going to use a normal thermometer. I'm going to use an uncalibrated thermometer. This is my little ship if I ever have to go to prison, you know. If you look at this, DJ, I saw somebody dunk last night who was not DJ. It wasn't on our team, actually. If you look at this, you can see the two sides are different, right? This has kind of bluish, this has kind of orange. The colors of the hated Broncos. By the way, let's look up here. The hated Broncos, by the way, is the team that we lost to last night, in case you're curious. What's going on right here?
That's the heat.
We are seeing the result of the heat. We have hot air, and the hot air actually has a different speed of light. Light travels at a different speed through it. And so the light from the projector is going through it because of the different speed, it's being deviated in different directions. And so we see the picture being messed up by that. Very cool. Now I'm going to take this and put it in the flame. And it burns. Okay. Never go far. How awesome is that, huh?
Wow. Whoa, I didn't look back.
What happened there?
Whoa. It got warped.
It got warped. That's a very good description. Because things warp, because as you heat them, they will expand. Almost everything expands when you heat it. This had two different types of metal. That's why I had DJ look at it, so we would have some verification. One type of metal expanded more than the other. You sheet it up again. Which side would you say expanded more? This side here or this side here?
First side.
This side. This side expanded more. You have two things that were straight. One expands more, and it's going to curve away from the longer side because they're bonded together. So by measuring how much this curls, you can measure the temperature. So this is called a bimetallic strip. Two metals bonded together. Now here's just some other fun stuff. Oh, okay, there it is. I have here a ring, or an annulus, and here I have a ball. The ball goes through the ring, goes away. Now I'm going to heat up the ball. What's going to happen to the ball as it heats up? It's going to expand. So what do you expect my demonstration is going to show? That what? Doesn't fit. How can I make it fit?
Heat up the ring.
Okay, did you guys like study this beforehand, or you guys just all know this already? I kind of feel like I've got Daniel in the Lion's Den going on here, you know? So when I heated it, the hole got bigger just like the ball got bigger. That's the important thing I actually want you to get out of this, that the hole got bigger when I heated it. Because you think, well, the metal expanded. Should the hole got smaller if it expanded inward? No, the hole gets bigger just like the ball did. Now this is always fun. It's called quenching. What's going on with quenching?
Rapidly. Not expanding. Yeah, contracting.
Now the metal is going to contract, but not enough for us to have an effect from it. But the water is not the same temperature as that metal was. And so that meant heat as we learned from the second law, naturally flows from the hotter one, the ball, into the colder one, the water. And so the water has a lot of heat coming in. Well, heat is energy flowing, so the average energy of the water molecules was shooting up for the water molecules right next to it. If they get a high enough average kinetic energy, a high enough temperature, the water molecules will break away from other water molecules and go into vapor. And so that was happening very rapidly. And so we were hearing the sound from all those water molecules suddenly expanding outward and making sound. Here's another type of temperature measurement. A strip you put on your forehead. And it's made out of a thermal polymer. A polymer, you guys, most of you say chemistry, you know about polymers. A polymer that's a thermal polymer is one that actually changes color with temperature. Very popular for mood rings, right? A mood ring is the same material, basically. And so they put this on your forehead and they have it adjusted with the right components so that the temperature will change different, the color will change at different temperatures here. And so you just look at where the temperature changes to determine, or where the color changes to determine your temperature. With the mood ring, if you're cold, it's going to be black. And as you get hotter, I think that's the way it is. And as you get hotter, it goes through a spectrum of colors. And so the mood ring is just measuring the temperature of your finger. Oh, I should point to this last one. This one here, he's measuring the radiation coming off of it. He's measuring the electromagnetic waves, light waves, except for these are in the infrared range, to determine the temperature. Thermal expansion, stuff expands when it gets hot. The basic equation is the change in length is the original length times some coefficient alpha, which depends on the material, so you have to look it up, multiplied by the change in temperature. If you have that, so that's length, that's one dimensional. If you have three-dimensional growth, if you have a heating and you're measuring the volume, then you have the change in volume is also roughly linear with temperature. I say roughly, they can't both be linear with temperature. The math doesn't work out. But it's very close to both being linear with temperature. And for most materials, that coefficient of volumetric expansion is just 3 times the coefficient for linear expansion. So when something heats up, it expands. We saw that phenomenologically. Now we're going to do a calculation. I'm going to have you do the calculation. Here are coefficients, and I'm going to write these numbers down that I circle. For gasoline, the coefficient of volumetric expansion is 950 times 10 to the minus 6th per degree Celsius. It's a very small change in volume per change in temperature. And then for iron or steel, the coefficient of volumetric expansion is 35. So those two numbers we're going to use in our problem coming up in a minute to do a calculation that's actually very fundamental and useful. It's something I've made a mistake with myself. This is just a picture showing that holes grow just as the material would. The picture is to illustrate that if I had a piece of metal and I drew this blue circle on it and then I heated it up, the blue circle would expand because everything's expanding. If I drilled out the blue circle and I heated up, that drilled out hole would expand exactly the same amount as the drawn circle did. So that's all this is. Now your problem. So your groups are, just a reminder, Wes, Trace, and Nate, Michael, Emily, and Max, Andrew, Sarah, and Kaylin, Mira, Ryan, and Lydia, Madison, Sarah, Clayton, and Sarah Kemp, and DJ, Leslie, and James. Well, DJ and Leslie. So here's our problem. Suppose your 60-liter or 15.9 gallon gas tank is made out of steel. And remember, steel, what was the coefficient of volumetric expansion for steel? It's full of gas. So both the tank and the gasoline have temperature of 15 degrees Celsius. How much gasoline? Beta for gas was 950 times 10 to the minus 6 per Celsius degree. has spilled by the time you reach 35 degrees Celsius. It's a real effect.
It's like full, and then it like
Steel gasoline tank. So we usually go in for steel. Yeah. Then it's full of gas. So do we?
Well, not the
That's
inflation. The one that's yellow.
yeah.
No, that was just gasoline. It's also
So when we have two, we just put out them.
the gasoline company on the speed as well. It's one of these now.
I'm like, why can't you just both?
Beta is equal to 3, so that's why. I think it's do not put beta times 2. That's beta.
Change your mind.
Sheriff's officer.
Yep. Okay, we have our first group is done, so come on up, gentlemen.
You want to talk? Write it down.
No, that's gonna happen.
Okay.
So we're doing the gasoline one first.
I'm just writing the equation. Okay. So that's the equation we used. So first we found the change in volume for gasoline. So for gas, it equals the initial volume
60 liters.
was 60 liters,
That's by the, yeah.
950. I don't have room, so I'm just going to put 950. And then the temperature change was 20 degrees.
Yes.
And that was about 1.14
Yeah.
liters.
Yeah. You put steel and the rest of it on the side.
Okay,
That way you have
Yeah, well-
space to see.
And for steel,
Same equation.
Yeah, same equation.
Yeah.
Just
how do I erase?
turn around. Yeah.
Whoa. All right. Got 60 liters and 35 times 10 to the negative 6. 20. We got
0.042.
0.042. So then the change And volume was the 1.14 liters, which was gas minus the 0.2 liters, steel, and we got 1.1.
1.098 liters of gas stove.
All right, and that's good. You can stop there. So notice that's a significant amount of gas that we spill. So if you have one place that's dispensing cold gas and one place that's dispensing hot gas, you're getting a lot more molecules with the cold gas than the hot gas because of its fairly large coefficient of thermal expansion, which is, I think, very interesting to note. And you just don't want to fill your gas tank up on a really cold night when it's going to be warm the next day, because I've done that, and then my garage smelled like gasoline because of the gasoline overflowing from the gas tank. Yeah.
Oh, you like